Okay, hello everyone. Uh, so as I said on Tuesday, which is yesterday, I will have a business travel tomorrow. So I'm going to record the lecture and then share through the YouTube. So let me share the screen. Okay. So I explained about what is the HN staining, and then there are heat effects depending on the temperature. And then I mentioned that this table is going to be very important for the kind of test. So the coagulation can happen when the temperature is going to be about more than 60 Celsius degree. And the vaporization will occur at the 100 Celsius degree of the water molecule. And carbonization is once the water molecules are all vaporized, and then the leftover tissue will be burned. And then they will be look like kind of black color, which is the carbonized. And if you have a more higher temperature, then the tissue can be melting down. So what happens during the thermal interaction? So when the light is illuminated to the tissue, the observers in the tissue will basically take the energy from the light, and then will be in the excited states, which is the A star. And then these excited observer materials are going to deliver that thermal, sorry, the excited energy into the surrounding molecules, which are having some energy of the kinetic energy. And then that excited state, the observer will uh, basically give the extra energy into that M material so that there will be a delta E kinetics, and which is the source of the heat generation. And then for the tissue case, the most important, the observer of the light is the water. And then due to the specific vibration frequency of the water, the highest absorption can occur at around 3 micrometer, but also it happens to around 2, and also about like 5, close to 5 microns. So thermal effects model are having three components. The first one is the heat generation, and the heat generation can be coming from the laser and optical parameters, and also the tissue optical parameters. So how strong the laser is illuminated, and then how large the tissue will observe the energy from the laser. And once there is a heat generation in the tissue, then second component is going to be how that generated tissue will be transported to the surrounding tissue. So for this step, the thermal tissue parameters are going to play the important role. And then those are basically heat conductivity and also heat capacity. And then depending on the how much of the temperature rises in the tissue, the effects is going to be also uh, depending on the temperature, but also that is going to be depending on the type of the tissue. So for the heat generation model, um, so we assume that the slab of tissue is exposed in the air, and then the laser is going to be illuminated to the tissue with a Gaussian shaped laser beam. And the electric field can be described as electric field magnitude multiplied with 2 of the exponential decay function. One is for the following the R, which is this direction from the surface of the tissue. And then the other one is the Z, which is the depth of the tissue, and the other one is the time. So as time goes, and also as the light is traveling in the z direction, and also depending on the r positions, so electric field magnitude can be described. Since intensity is following to the proportional to the square of the electric field, so you can see that there is um, two uh, r happen here. So 4 becomes 8, and r becomes to 2r squared, and then the 2 will be disappeared at here. So at the position of the r is the same as the w, which is the radius of the beam width at the focal distance. And also when the time is 0, then basically from this equation you can see if you put the r as a w and then t as the 0, then basically disappear as a 1, and then z is also at this point 0, then disappear. Left over is going to be 1 over e squared of the I sub 0. Or when the t is the tau over 2, here the tau is the pulse duration time. So when the time is half of the pulse duration time, and also the position of the r is 0, and also the z is 0, then the intensity at the point here is going to be also 1 over e squared. So the relation between the E sub 0 electric field and the light field intensity is shown on here. And as I said, is proportional to the electric field square. For this heat generation model, now we are ignoring the scattering property of the tissue, because the scattering itself is going to basically change the direction of the light propagation in the tissue, so that to account for all the change in the direction will be really difficult when we are making the model. So at this moment, the scattering has been basically assumed as 0. And the heat will be generated during the laser exposure, and then the deposition of the heat, which will be coming from the absorption of the light in the tissue. So light flux in the z direction, the local heat deposition per area and per time in a thickness of the delta z can be shown as a S. So S is the local heat deposition, and then they can be described as a difference between the light intensity at the position of the z and the z plus delta z divided by the delta z. So if you look at that, as the delta z is going to be close to the 0, it's like something like when we were learning in the mathematics for the making the limit. So in that case, this s is following the negative of the kind of differentiation. So round I over round z. So from the previous equation, you can actually also see that this I, which is the light intensity, can be described as like this one, right? In the previous slides. So when you are making the differentiation of this I with respect to the Z, then basically the leftover is going to be I sub 0. And then there will be minus alpha is going to be coming in front. So the I round I over round Z is going to be basically same as the alpha IRGT. So heat deposition is now shown as this value. So here the alpha is actually absorption coefficient. So assuming that there is no phase transition, such means that the no vaporization or no melting happens during the laser exposure, or the tissue alteration, such as the coagulation or carbonization. So we are also assuming that there is no change in the phase from the liquid to the gas, or no tissue alterations, such as the coagulation or carbonization. In that case, the change of the heat content, dQ, will cause the linear change in temperature, dT, by following the thermodynamics law. So dQ, basically heat content change, is going to be depending on the mass of the tissue, and then C here is the specific heat capacity, and then dT. So when there is a change of the temperature, and then they can be also directly related to the heat content, which is making sense. So when there is a more heat content, then there is a more change in the temperature. But there will be depending on how big the tissue mass is, and also how big is the specific heat capacity for that tissue. And Takata in 1977 showed that the approximation of the specific heat of the most of the tissues are given by the following equation. So here, the rho sub W is the water content, and then which is actual density, and also the rho is the tissue density. So basically, it means that what is the water amount in a tissue volume. So in the case of the water, basically this will become 1, so that the C is going to be simply 4.35 at the temperature of the 37 Celsius degree. So the previous equation of the heat content dQ is mc dt. This equation also describes the relationship between temperature and heat content within a closed physical system. So this is also important, which means that when there is a heat generated, and then there is no heat dissipation from that location. But in the real life, there are losses of the heat as well. So heat loss is basically following or happening due to the heat conduction, and also heat convection, which is the case of heat transfer due to the blood flow, and also heat radiation. But for the heat convection and heat radiation in the tissue, both of them can be actually ignorable. Uh, because heat convection is very minimum due to the low perfusion rate of the tissue, so that it can be ignored. But if you are having long exposure, and also in the laser-induced interstitial thermotherapy, which is LITT, then the heat convection also can play the important role for the heat loss. So this table is showing the blood perfusion rate of some kind of organs. And you can see in the fat tissue, the perfusion is very, very low. Muscle is a little bit high, and the skin is heavy high, but the brain is also 0.46 to 1. So, however, probably the most well perfused organs are the kidney and also the thyroid gland. They are showing about 3 or 4 milliliter per minute per gram of the tissue. But for the most of tissues, heat convection can be ignored. And the heat radiation is following the Stefan-Boltzmann law. And then this law states that the radiated power P is going to be equal to the surface area and then epsilon, which is the emissivity of the tissue. And that this value is compared to the black body and then less than 1. And also the sigma, which is the Stefan-Boltzmann constant, and the T. So here, as you can see from this, to have some noticeable radiative power from the heat radiation, the temperature must be very, very high because this sigma value is very, very small. It's 10 to minus 8. So unless you have a very high temperature, this heat radiation can be actually also ignored. So the leftover one is the heat conduction. So heat conduction is the main source of the heat loss. And then this allows the heat can be transferred from the light exposed area to the light unexposed tissue. So when we look at the Fick's law or the diffusion equation, the heat flow is proportional to the temperature gradient. So here described as a J sub Q, heat flow can be described as a minus of the K, which is heat conductivity, and then del of the T. So here del of the T is a three-dimensional divergence of the temperature. So let's go back to the Fick's first law because we need to look at this first. So at the steady state, the J, which is the diffusion flux, and in other words, that is the amount of the substance per unit area per unit time. They can be described as minus of the diffusion coefficient, and then following the concentration change along with the X. This one is for the one-dimensional case. But if we are expanding this to the 2 or 3 dimension, then we need to have the del of the phi. For the second law or the Fick's second law is basically showing that the concentration change per time can be described as a diffusion coefficient and then double differentiation of the concentration along with the space. So here, since this is for the one dimension x, and then converting that into the 2 or 3 dimension, we can use this delta. So the phi. So this is representing actually d multiplied with a delta and b. This represents the Fick's second law. So Takata at 1977, he also showed that the heat conductivity K is following this equation, 0.06 plus 0.57 multiplied with the rho sub W divided by rho, which looks very similar as the previous equation. So for the case of the water, they are same. So simply for the water case, the K, the heat conductivity is 0.63 at the temperature of 37 Celsius degree. So temperature conductivity, or in other words, thermal diffusivity, can be described as shown as a kappa, and this kappa is basic heat conductivity divided by the density of the tissue and then heat capacity of the C. So the dynamics of the temperature behavior of the certain tissue type can be expressed with the K and also heat capacity C, so that this thermal conductivity kappa can be shown as a K and also rho and C. Interestingly, the value of the kappa, the temperature conductivity or thermal diffusivity, is approximately same for the just liquid water and also most of tissue. And the value is 1.4 times to 10 to minus 7 per meter square per seconds, which is shown by the Bohr-Noyce in 1986. Um, actually, um, you may feel wonder, how come the water and then just most tissues are behaving same kind of thermal conductivity? But when you look at this equation, you can see that when there is a K is going down, so heat conductivity going down, and then actually heat capacity is also going down. So when the water content is becoming low, then heat conductivity value is going down. At the same time, the heat capacity is also going down. So since numerator denominators are both are going down, so that the kappa value is actually showing kind of same number regardless of the change in water content in the tissue. So let me also tell you about the equation of the continuity. So the temporal change in the heat content per unit volume, which is shown as a Q dot here. This Q dot is determined by the divergence of the heat flow, which is shown as a J sub Q. So divergence of the J sub Q can be shown as minus of the Q dot. And then this negative sign is representing the sink of the heat, basically heat loss. So when we look at the divergence, this divergence measures the magnitude of the source or magnitude of the sink at a given point in a vector field. And then basically from the vector information, converting that into the scalar value. So for example, when the air is heated, it can be shown as a plus positive. When the air is cooled, then it can be shown as a negative value. As a basically negative represents the sink, and the positive is representing the generation of the heat. So when we are saying the x and y and z as the Cartesian coordinate system for the three-dimensional Euclidean space, and also I and j and k as unit vectors for each x, y, z, then the divergence of the continuously differentiable vector field F can be shown as a ui and bj and the wk. And this is basically equal to the scalar value function. So divergence of F is del dot F, and then they can be shown as a round U over round X, round V over round Y, round W over round Z. So when we are inserting divergence JQ is minus Q dot into the previous equation showing it about the heat content equation. So by putting that into here, so we can see the T dot is 1 over MC and then Q dot. Since the Q dot, since the M is the density multiplied with the volume, and then, so this is the 1 over rho C, and then Q dot over volume, which is the basically representing the lowercase q in the per volume. And then since the q lowercase q dot is same as this divergence jq, so you can have a minus here and the divergence j sub q. And also the diffusion equation of the j sub q is minus k del t into this equation. Then t dot is shown as a kappa, and then delta t, because the kappa is the k over rho and c. So here is the delta is the Laplace operator. So T dot is kappa and the delta T. And this is the homogeneous heat conduction equation with the temperature conductivity, which is shown here as a kappa. So Laplace operator, which is the there, this is a composition of the divergence and also gradient operations. So converting scalar to the scalar, and then the delta F is the del square F, and that is also same as the del dot del F. Um, let's say that when there is additional heat source S, such as the absorption of the laser radiation, then the previous equations of the 3.8 and 3.9, which is this one, so 3.8 and 3.9, they can be expanded into the 3.10 and 3.11. And then this is basically inhomogeneous equation. So you have terms of this and also this from the previous equation. So solving the homogeneous part of the heat equation, which is the equation 3.9, this one. Let's take a look at that first. So T dot is a kappa delta T, and this describes the temperature decrease after laser exposure, and then that is because of heat diffusion. And then in the cylindrical coordinates for the 3.9 equation, which is this one, can be expressed as T dot is a kappa, and then delta T is basically 3 dimensions. So R here, and then the phi and also Z for the cylindrical coordinates. So the general solution for the 3.12 is shown in 3.11. So temperature at the position of the R and the depth of the Z and the time of the T can be obtained as T sub 0, which is the initial temperature, and then psi sub 0, which is the integration constant, over 4 pi and the kappa and T over 3 over 2 to the power, and then exponential decay function, which is the R square plus Z square divided by 4 times kappa T. And then you can check the proof of this in the textbook. And then solution of the inhomogeneous heat conduction equation, which is the 3.11, this one, which contains the 1 over rho C and then S. This is strongly depending on the temporal and also spatial dependencies of this S. So heat loss here. So it is normally numerically evaluated with the sum of proper initial value and boundary conditions. And then you can also check the textbook for the derivations of this. So the spatial extent of the heat transfer is described by the time-dependent thermal penetration depth. So Z therm means that thermal penetration depth at the time of the T can be shown as a square root of the 4 times kappa and T. So if you are square for both of them and then moving this 4kT into here, you will get this equation. Here, this G term T is actually representing the distance from the surface, which the temperature is decreasing to the 1 over E, which is about 37% of the peak value. So assuming that that is going to be when the Z position is 0, it will be having the highest value of the temperature. So when we had a cylinder of the tissue, and then we had a laser exposure in this area. And then when you look at the temperature along with this G direction, then the temperature will be decaying like that. So the surface will have a highest temperature increase, and then if you see, which is the about 37% of this peak value, then this distance is basically G term, and then that is called as a thermal penetration depth. So this is actually very same as when we were discussing about the absorption penetration, light penetration depth, when there is only absorption or scattering. So light intensity is going to be decreased, and then this is going to be, the slope is going to be depending on UA and also US, which is the attenuation coefficient, mu sub t. So here we also look at the penetration depth of the light um, as 1 over E point of the light intensity at the surface. So here same as the temperature. So this thermal penetration depth of the water, if you look at this, is going to be depending on the time of the laser pulse. So when you have a 1 microsecond pulse, thermal penetration depth is going to be about 0.7 micrometer. If you are giving the more longer and longer exposure, not exposure, but pulse duration time, you can see the thermal penetration depth is getting also longer and longer. And if you give 1 second, it's about 0.7 millimeter. So from the 1 microsecond to the 1 second, there is a 10 to 6 times of the increase in the pulse duration time. And then same thing also happens from the penetration depth, also increasing from 0.7 micrometers to the 0.7 millimeter. Okay, so it's not exact 10 to 6, but this is the 10 to 3. So 1,000 times increase here. So that's the square of 10 to 6 is going to be also shown on here, which is the following this square root. So when there is a time increase of the laser pulse duration, then the pulse penetration depth is following the square root of the time increase. And then the kappa here is basically thermal diffusivity, as we mentioned before. And then that is actually very same for the either liquid water or most tissues, and having a value of the 1.4 times to 10 to minus 7 meters squared per second. So that means when you have a tissue and then you give, let's say, 1 microsecond pulse of the laser, and then the temperature, let's say this is the temperature, and then this is the initial or maximum temperature at the surface. This will go down very quickly, and then 1 over E point is following 0.7 micrometer for the 1 microsecond. But if you are having 1 second long like that, then this decay is also very, very slow, and it will be something like that. So that 1 over E point is basically here as a 0.7 millimeter. So simply, let's say that the surface temperature was 100 Celsius degree, and then 37% is going to be corresponding to, this is 37 Celsius degree. So when you had 1 microsecond pulse of the laser, then the 37 Celsius degree can be obtained when you measure from the zero point 0.7 micrometer from the surface. But when you have increased pulse duration time to 1 second, then at the depth of the 0.7 millimeter, you have a 37 Celsius degree. So as you can see from this example, this means that for the 1 microsecond, any thermal effects will happen less than 0.7 millimeter from the surface, or less than 0.7 micrometer. But for the 1 second case, it will be 0.7 millimeter. So that means that there will be like 1,000 times more deeper tissue will be affected by the temperature increase due to the laser. So 37 is simply our body temperature, so it is safe. But when you look at the 60 Celsius degree, they will be corresponding to around here. And then at that 60 Celsius degree, the coagulation will occur. And then if you look at that, like same here, then you can also see that how deep the tissue will be coagulated when you are increasing pulse duration time. So this is representing that the 1 microsecond is 0.7 micrometer, which is very shallow. So that's why it is actually showing that the 1 microsecond rule of the pulse duration time is coming out from here. So when you have a longer than 1 microsecond, then you will certainly have any thermal interaction. But when you have a shorter than 1 microsecond, then you can minimize that thermal interaction um, from the site of the laser irradiation. For the thermal decomposition of the tissue, so it is important to adjust the duration of the laser pulse in order to minimize the thermal damage to the adjacent structure, which we have seen in the previous examples. So the scaling parameter for this time-dependent problem is called as thermal relaxation time. And then if we are making the same between optical penetration depth L and then thermal penetration depth G term. So this will happen when the time is going to be in a tau term. So what the mean is when you have a tissue, and then you can look at that as the depth of the Z. One is looking at the light intensity point. The other one is looking at the temperature profile along with the Z. So when you're looking at the optical penetration depth, then that is basically I0 is going down within the tissue, which is following the attenuation coefficient, and then 1 over E is going to be corresponding to this L. And the temperature will be also going down, and then 1 over E point will be basically Z term. And then this Z term is going to be also affected by the time. So when you have a longer pulse duration time, then you have a very long here. When you have a short pulse duration time, this curve will be getting shorter. So when the T is the tau term, and then that point, Z term is same as the air, and then that tau is basically thermal relaxation time. This tau term, which is the thermal relaxation time, is measure of the thermal susceptibility of the tissue. So when this tau term is smaller, then basically thermal susceptibility is shown as increase, which means that short. Then basically the tissue is going to be affected easily by the thermal uh, damage. When this is very long, actually, then this is reversed actually. So when the tau term is very short, then the thermal susceptibility is low because it will have a minimum of the tissue damage. When the tau term is long, then basically that means that the tissue will have a more damage due to the that thermal generation, heat generation by the laser. So how long it will take for the temperature at depth Z to reach the 1 over E of the temperature at the position of the Z0. This is also basically explaining about what is the thermal relaxation time. So other words, this gives the indication of how long it takes the heat to travel to the distance at Z. So the thermal relaxation time gives the indication of how quickly the object loses its heat. So again, same thing, tissue here, and then we have a heat as generated when the laser is coming here, and then this ray goes down along with the z-axis. So if this tau term is smaller, that means that it comes here. And then when the tau term is kind of long, then basically that means that it takes longer time for the heat to travel into the z direction. So how fast the heat travel to the distance is actually same as how fast heat will be lost. So it will be also shown as in the LITT section. So the relaxation time is basically giving us some idea of whether it is important to include thermal diffusion in our calculations or not. For the processes or events that happen much more quickly than the relaxation time, then we can actually ignore the thermal diffusion. So when you have a thermal relaxation time is shown here as maybe like 1 microsecond. So that means that for the heat, highest temperature T sub 0 to be in the 1 over E of the temperature of the T at this time point. No, I think that this is not right. So in the previous equation, previous slide, so we have seen that this tau term is the thermal relaxation time, and then that means that it represents time for the temperature um, drops into the 1 over E point. This is a G term, and this has to be matched with the optical penetration depth. So if this thermal relaxation time is short, that means that um, when the light is going in to the tissue, for the penetration depth, it goes into the air depth. And then if the this thermal resistance time is short, means that within the very short time, the heat transfer from the surface into this air position is very quickly done. But if this tau term is increased, that means that for the heat generated from the surface and then conducted to this air point, it takes longer time compared with the smaller the thermal relaxation time. So let's say another example, if the air is maybe 1 millimeter, and then if you have a smaller thermal relaxation time as maybe let's say simply 1 microsecond, and then if you have another tissue which has a longer thermal relaxation time as 10 microsecond. So that means for the 1 microsecond case, this means that um, after you give the laser exposure, and then 1 microsecond after the laser irradiation, then the temperature at the air position will reach to the 37% of the surface temperature. But when you have a 10 microsecond relaxation time, that means that after you give the pulse of the laser, it takes 10 microseconds for the air position of the tissue to have a 37% of the temperature at the surface here. So this case is very slow heat conduction. For the 1 microsecond case, that represents very fast heat conduction. So smaller value of the thermal relaxation time means that fast conduction, so that it will also have a fast loss in the heat. If you have a longer relaxation time, it means that taking a longer time for the heat conduct from one point to the another point. But that means that from here to dissipate the heat to the surrounding tissue, it will also take a longer time. So anything happen smaller than relaxation time, then we can ignore the thermal diffusion because it happened very quick. So that before the heat is going to be conducted to the surrounding tissue, but that event is already stopped. So that we can ignore the thermal diffusion. For the laser pulse duration tau, if this laser duration time tau is smaller than this thermal relaxation time, then basically heat does not even diffuse to the distance to the air. So again, this means that when you have a tissue and then you have a air as a light intensity, goes to 1 over E point, which is 37 point. And this is the optical penetration depth. So that means that when you are giving the light to the tissue, then the penetration depth is basically air. So for the air depth, the light is relatively delivered, right? So that's the air. And then if the laser pulse duration time is tau, so you are giving the laser pulse with a tau duration time. And then this tau is happen to be smaller than the thermal relaxation time of this tissue. This tissue needs to have a tau therm so that the heat can be delivered, or basically heat can be conducted from the surface of the tissue to the depth of the air, right? But if the pulse duration tau is smaller than the thermal relaxation time of this tissue, that means that let's say laser which has been irradiated to the tissue from here, and it can penetrate to the depth of the air with relatively kind of high intensity to the tissue here, so that this tissue will start to generate the heat, and that heat needs to be traveled or conducted to this G direction. But if the tau is smaller than its relaxation time, then the temperature start to conduct from here to this point of the air, and it takes tau of the therm. But if you stop basically light illumination, just giving only tau, then this basically heat generated from the surface of tissue is start to conducted through this direction. But since the laser pulse is already stopped, so there is no more heat generation is happening at the surface, so that the tissue in the up to the depth of the air is relatively kept as safe, or beyond this air of the tissue is going to be not affected by any of the temperature happened in the surface of tissue, because there was no time for the heat transfer from the surface to the even this air position. But if you are giving very long pulse duration time, longer than the thermal relaxation time, then the finally heat is having enough time to diffuse into the tissue, and then it will be multiples of the air. So we can consider this as like that. So light intensity is reducing to 37% from the surface to the air position. So this is the optical penetration depth, which means that when you are giving the light will be penetrating the tissue in the depth of the air. So that's the kind of definition of the optical penetration depth. So this air is the depth that when you are giving the laser to the tissue, so the tissue will be basically absorbing most of the light energy up to this air position. And then if you are having the tau therm, let's see. So let's say again, tau therm is 1 microsecond. So if you are giving the laser pulse with a shorter than 1 microsecond, then the heat will be basically transferred from this point and then moving into this G position. But since tau is smaller than the tau therm, which is 1 microsecond, the temperature conduction is actually cannot be reaching even into this air position. So it stops at here. And then whatever you have effects of the laser to the tissue is going to be maximum in the depth of the air. And in this case, within the depth of the air, the further longer than the air, you have no effects of the heat generated by the laser. But when you are giving the longer pulse duration time, such as maybe you are giving 2 microseconds of the pulse, then optical penetration is same as the air. However, since you have a longer pulse duration time than the thermal relaxation time of the 1 microsecond, now you have a 1 microsecond heat will be transferred into this air position, and then you have an extra 1 microsecond. So the heat will be transferred from the surface to the depth of the air, and also another depth of the air. You can actually have a heat delivered into this position. So that means when you were giving the 2 microsecond pulse of laser to the tissue, then not only those optical penetration depths of tissue will be affected by the laser-induced heat, but now you have a 2 times longer or deeper tissue will be affected by the heat generated by the laser. So thermal damage can happen in the tissue, not only within the decomposed volume by the thermal. So this volume will be basically affected by the laser generated heat, so that the thermal decomposition can happen in here when you have a shorter pulse duration time. However, when you have a longer pulse duration time, then surrounding tissue will also have some leftover heat will be transferred, and then this tissue area can be also affected, such as the coagulation. So when you look at the thermal relaxation time as a microsecond scale, you can also see that around 3 micrometer wavelength, that is about 1 microsecond. So if the pulse duration is less than 1 microsecond, then it does not cause the thermal damage to the surrounding the tissue volume, other than the tissue volume which is having the optical penetration depth. So that's why we are calling as a 1 microsecond rule. What the mean is, when you have a shorter than 1 microsecond as a laser pulse, then that does not really cause any thermal damage to the surrounding tissue. But when you have a longer than 1 microsecond, then the surrounding tissue will be also affected by the laser pulse. The exception is this one is basically working for the single pulse laser irradiation. But if you are repeating the pulse, and then it can actually accumulate the heat. And then finally, the surrounding tissue will be also affected by um, multiples of the single pulse, even though maybe single pulse is not uh, longer than 1 microsecond, which you can also see in the LITT slide. So so when the laser is coming as a Gaussian beam to the tissue, and then um, it will be damaging the tissue like that. And then the depth will be kind of following the optical penetration depth. And then because of the Gaussian shape, it is going to be basically um, decomposing tissue in this volume. So if the pulse duration is shorter than the thermal relaxation time, in this case, water is 3 microsecond for the 1 microsecond. So if the pulse duration is less than 1 microsecond, then only this tissue part will be basically decomposed and gone. But if you have a longer than the 1 microsecond as a pulse duration time, then the heat generated from this tissue has enough time to transfer to surrounding tissue, so that this laser pulse will not only decompose the tissue here, but also going to affect the surrounding tissue, maybe around here. That depends on this boundary is basically representing the coagulation tissue. So at least this blue region, they had a temperature higher than 60 Celsius degree. So let's take a look at the case that when the tau is smaller than 1 microsecond. So the examples will be nanosecond laser or picosecond laser. So in this case, heat diffusion during the laser pulse can be ignorable. So with the assumption of the laser intensity is constant during the laser pulse, then the S at the R and Z and T is basically alpha and then light intensity value. So heat sink. So from here, you can see basically S is going to be the attenuation coefficient of the tissue, or actually here the absorption coefficient with the light intensity maximum value at the surface. So the temperature at the tissue surface, which is R0 and Z is 0, then the temperature can be described as two parts. So during the laser irradiation within the T as a pulse duration time, then the temperature will be increased as the initial temperature plus absorption coefficient multiplied with the I0 over rho and C, and then time. Once the laser time is the longer than the pulse duration time, then it will be following T0 plus T maximum value, and then following kind of slow decay is function of the tau, and then over T with a 3/2 to the power. Here, the Tmax is representing maximum increase in temperature. And this will be basically when the T is the tau at the end of the first duration, then Tmax will be basically this. So let's take a look at the graph. So when you have a 100 microsecond for the first duration time, and then the temperature is going to increase depending on the energy. So here you have the same time. So this increase in the energy means that increase of the laser power. And then once you stop laser pulse at the 100 nanosecond, and then temperature will be will start to going down. And then this kind of pattern is following this tau over t 3 over 2 to the power. So since first duration time is shorter than 1 microsecond, so that since our tissue has mostly water, so the thermally damaged zone is smaller than optical obtrusion length, so that the surrounding tissue will not be actually having any thermal damage. When the tau is longer than 1 microsecond, then finally heat diffusion is going to happen, so that the thermal damage zone, this zone can be broadened, not only within the optical penetration depth, but much deeper than the optical penetration depth. For the case of the heat diffusion, when the tau is longer than 1 microsecond, it's hard to get the analytical solution from the inhomogeneous heat conduction equation, which you have seen in the previous slide. So instead of using analytical solution, you can use the numerical solutions. So for using finite difference technique or recursion algorithm, which is actually talking about the same thing, this can be used to simulate what is going to be the temperature when you have a longer than 1 microsecond pulse. So here you can see the examples. It's very long actually. So laser on for the 10 minutes. And then you can see the temperature is rising maybe up to close to 60 Celsius degree to cause the surrounding tissue to be coagulated. And then when you turn off laser, then the temperature is going down like that. This right side graph is also explaining about that one, but this will actually come again at the LITT. So I can explain this graph during the LITT part. So let's take a look at the examples of this the thermal interaction. It can be used as a point Weinstein treatment. So you can see in this example, the girl is suffering from this point Weinstein on the face, and then these two ladies or three ladies are also having this big area as a port Weinstein, which make the patient to avoid their life at the maybe outdoor. So one way to treat this port Weinstein is basically called as a photothermolysis. That is because the microvessels on the face are normally having smaller diameter, but those proton stained tissue are having enlarged capillary. So dilated proton stained vessels are in the range of the 50 to 150 micrometer, which is supposed to be between 10 to 30 micrometer. So this enlarged or dilated the blood vessel is basically shown on the surface of the skin. Since blood has a high absorption in the 577 nanometer, so you can use the dye laser. And then for the kind of blood vessel, it follows a cylinder shape, right? So it is kind of cylinder shape of the blood vessel. And for the thermal relaxation time for the cylinder case, which is actually from the water, um, and then cylinder type, this follows the d square over 16 kappa. Here d is the diameter, and the kappa is thermal diffusivity, which is the fixed value. So when the diameter is longer or larger, then the tissue relaxation time is actually increased by square of that diameter increase. So if there is a, let's say 10 to 50, like 5 times, then the relaxation time is 5 by 5, so 25 times more longer compared with the small blood vessels. So here, for the 30 microsecond, it will be 0.4 millisecond for the relaxation time. But if the blood vessel diameter is 150 micrometer, then the time is about 10 milliseconds. So that means that for the smaller blood vessel, it takes only 0.4 millisecond for the heat conduct from the original position to the optical penetration depth. But for the 150 diameter, it takes 10 milliseconds for the heat to be transferred into the optical penetration depth. So by choosing the proper duration also between each pulse, then we can actually selectively cause the coagulation. So here the key point will be we need to have a duration between each pulse to be longer than 0.4 millisecond so that all the heat generated from this blood vessel will be dissipated to the surrounding tissue, and then shorter than 10 microsecond. So in that case, the heat generated in the blood will be remained here, and then but the small blood vessel heat will be actually dissipated to the surrounding tissue so that this will not be damaged. So we choose the irradiance of the laser to deliver enough energy for the coagulation. So you are seeing this example here, large blood vessel here, and then small blood vessels are here. So when you look at the top case, when you are giving the short duration between pulses, and then you have a high power, then the heat has no time to diffuse from the blood vessel, so that both of blood vessels will be coagulated. So this is the critical temperature that will cause the coagulation. So high power and a short the time between the pulse, so that both of them will be affected by the laser generated heat, so that it will be coagulated. For the bottom case, you have a low power, and then you are giving long duration between pulses, so that both of blood vessels are having enough time to dissipate heat to the surroundings, so that they will not be coagulated. But if you choose the medium power, And if you choose the duration time between those two thermal relaxation time, then these small blood vessels will have a fast transfer of the heat to the surrounding tissue so that this will not be coagulated. But large blood vessel uh, doesn't have time to dissipate heat to the surrounding tissue so that the temperature is going to rise higher than the critical temperature and then start to be coagulated. So that by having this way, you can selectively choose the large blood vessel to be coagulated, and then eventually this blood vessel will be disappeared as time goes. So let's take a look at this hair remover example, and then you can maybe understand much better. So this is using the difference in the thermal conduction or relaxation time between the skin and hair. So by controlling the pulse duration time itself, and also by controlling the pulse repetition rate, which is related to the pulse, the time between the pulse duration. So you have a pulse duration time and then pulse repetition rate. So this is representing the pulse duration time, and this is the duration time between the pulses. Let's say this is tau 1 and tau 2. So this will be the whole single, how can I say, pulse, and then with the resting time. And then let's say this is the tau 3. And then so if you are dividing 1 second with the tau 3, then it will give the hertz. And then this will be the pulse repetition frequency. So let's say that if the tau 3 is 1 millisecond, and then within 1 millisecond, maybe you have a 0.1 millisecond, which is the 100 microsecond as a pulse, and then tau 2 is 0.9 millisecond as a waiting time between each pulse. Then you can have a 1 second divided by 1 millisecond, so you can have a 1 kilohertz as a repetition rate. So by controlling pulse duration time and also by controlling pulse repetition rate. So if you have a same pulse duration time, but if you increase the pulse repetition time twice, that means that you have to sacrifice this 0.9 second to be 0.4. So that overall it will be 0.5 from the 1 millisecond. Then you can have a 2 kilohertz. Okay, so let's watch this video, and this explains how we can selectively remove the hair by using the laser, but keeping the skin to be safe. I hope this video is also recording the sound.
Conduction time.
Okay, so with this, I will close for the today's lecture. And then actually there are about 20 more slides left for the thermal interaction, which will include the laser-induced thermotherapy. And then we will continue to explain about those after the next week, so that we will see each other on 27 Tuesday. So hope that you enjoyed this video, and then we can see on 27. Okay, take care and bye.